Hello, it's Dr. Wyatt, and I would like to give you a little background on our late lunar forming impact simulations. The giant impact hypothesis was introduced by Dr. William Hartman in 1975. The moon has several strange properties. It's relatively large compared to the Earth, like satellites of Jupiter and Saturn and the other planets are small compared to their parent planet, but the moon is large enough to actually be a rocky planet. Now, the rocky planets, when I'm saying rocky planets, I mean Mercury, Venus, Earth, and Mars, the planets that were inside the asteroid belt. And you have the gas giants that lie outside the asteroid belt. Well, the moon is larger than most satellites compared to their parent planet. And another property about the moon is that it has relatively little iron. Now, all the rocky planets have large iron cores. So what they think happened was that two of the rocky planets slammed together, their iron cores coalesced, and they spun off enough rock and debris around the two iron cores, and this later coalesced into what is now the moon. And since it was made of all the rock and debris outside, it has a relatively small amount of iron in it. Now, this is Dr. Canop's simulation. Dr. Canop is the lead researcher in this project in the world. And here's one of her simulations. Now, I had two students come to me, Brett Hoker and Justin Highland, and they want to see if they can simulate this. So I sent them to supercomputing to learn about computing, and they came home with information about NVIDIA graphics cards. So we wrote NVIDIA. They gave us a donation of two video cards. Mellanox Technology gave us a donation of some switches, and a provost gave us a donation, and we started the High Performance Computing Lab to work on this project. Well, here's their first stab at it to see if they could reproduce what Dr. Canop had done. And they did this in one semester. They didn't know C when they started. They didn't know CUDA. They learned CUDA and learned C and built a computer and came up with this simulation, which looks relatively similar to what Dr. Canop's simulation looks like. Now, what all the people do when they create these simulations is they do a slam and then have the slam produce a disk of debris. Now, the disk of debris, they never have coalesce into a moon. They cite this paper from the University of Tokyo, which starts with a disk of debris and then has it coalesce into a moon. But it's two separate simulations. So Brett and Justin want to see if they could simulate what the University of Tokyo did. So here's their attempt at that.
Well, it's a marvelous night for a moon dance with the stars up above in your eyes. A fantabulous night to make.
And if you watch this video long enough, all the debris does coalesce into a single moon. So they were able to reproduce what Dr. Canop did and what they did at the University of Tokyo in basically a year and build a supercomputer or a really high-performing desktop computer. Now, what we didn't like about this is it's done in two simulations with different parameters. And we want to see if we could do it in one simulation with the same set of parameters. So have the two rocky planets collide, produce a disk of debris, and have that disk of debris coalesce into a moon. And so I had two new students take on this project. It's Travis Cizillo and Justin Island. And here's their attempt at that. And if you notice, the simulations have gotten a little more sophisticated. This one's 132,000 bodies.
Stop the world and let me down. I'm tired of going round and round. I played the game of living loud. So stop the world and let me out. bonds are shattered, don't you see? Now you no longer care.
Now, if you watch the simulation long enough, it will produce a single moon that is of the right size. But if you look at CANOP simulations and Hoker and Justin's simulation and Travis and Justin 2's simulations, you'll notice something, that the disk of debris is created completely from the impactor. None of the debris comes from the planet that got struck by the impactor. Now, this causes a problem because we have dirt from the moon and we have dirt from the Earth, and their isotopic properties are almost identical, which this means like the isotopic properties. Now, some of the stuff like the volatiles got boiled off, but things that didn't, their isotopic signatures are almost the same, and that makes it us think that both the moon and the Earth had to both come from the same parent material. So having the moon come strictly from the impactor was improbable. So here's how CANOP addressed the situation. She produces an impact where both impactor and target sling off enough equal amounts of material, and then that material is what creates the moon. And here's Travis and then this is what Harvard did. So what Harvard did, they took a fast-spinning planet and slammed an impactor into it, and they got a large amount of both the impactor and the target material outside the Roche limit there to create what would later become the moon. And so Travis and Justin wanted to see if they could do this. So here's their attempt at this. And so they did the same thing basically as CANOP did and Harvard. They put spins and had both impactors of equal size hit. And they did it independently. They didn't find out about what CANOP and what they'd done at Cook had done at Harvard until after they'd done this simulation. But if you watch this entire simulation, you'll get a moon made of equal parts from both impactor and target. And what they added to it, they actually got the actual axial tilt of the Earth. The Earth doesn't, the moon doesn't rotate around the Earth in the ecliptic plane. The moon rotates around the Earth in an off-ecliptic plane. Now, another problem that arises from all these simulations, that all the simulations, Harvard's, CANOP's, and ours, have basically twice as much angular momentum as they should have, and this causes a big problem. So what Harvard suggested is that there's a thing called evection resonance that remove this angular momentum from the Earth-Moon system. But the Royal Society in 2013 called a meeting and rejected evection resonance as a viable means for removing the excess angular momentum. And on the cover of Nature magazine, they said, lunar forming theories found wanting, bring on the new models. So I had a new group of students. I think this is Taylor, JPEG in the back, and Ty back in front, Jared, Ed, and Baylor. This is us at not supercomputing, GTC in 2016. And the guy in the back is a gentleman that we met at supercomputing that we hung out with. Not supercomputing, GTC. So what we did to address this problem was we looked at the angular momentums of both planets that were colliding and the angular momentum of the collision. So if you notice in A, all of the angular momentums line up. Now this is great. This was the second simulation that we did, Justin and Travis had done. And what's nice about this one is it throws out equal amounts of material from both of the impacting planets. But since all of the angular momentums align, you can't adjust the angular momentum. You're going to get what you have. And to throw up enough material out into space to create a moon, the angular momentums are just too high. Now, the very first simulation they did is in B. So they took one of the impactors and had its angular momentum opposite of the angular momentum of the collision and that of the other planet. Now, with this one, you can control your angular momentum, but you'll only get material out from one of the impactors, which doesn't address the isotopic problem. So you can get the isotopic problem without the angular momentum done in A. You can get the angular momentum, but can't get the isotopic probably using the conditions in B. So what we decided to do was we will take both impactors and have their angular momentum opposite of the angular momentum of the collision. Now, we're a little skeptical at first because what will happen is both impactors are spinning into the collision, and there'll be nowhere for material to go except explode. But we thought we'd try it, and here's what we saw. It basically exploded like we thought, but there was enough material slung into orbit that a moon could form. And if you notice, the material that's slung into orbit is both blue and orange, so it means it came from both impactors. Now, we didn't quite get enough material slung into orbit, and so what we did next was we got them, so to not be a completely planar collision, we raised one up and moved one down, so it's a little off-planar, and that actually, too, give us a little axial tilt of the Earth because the Earth doesn't spin on its axis in the ecliptic plane. So that'd be positive, and hopefully we get a little more debris slung into space. And here's that collision. And if you watch this collision long enough, here's what you will see. You get a single moon made of almost 50-50 material from both impactors. The angular momentum is spot on. And so here's the final for that collision. And let me show you this next slide. What we're after was an iron poor moon. Well, our moon had no iron in it. Isotopic similarity. Our moon had equal parts from both impactors, so we satisfied that one. Angular momentum was spot on. Now, some other things we weren't really after, but just kind of came out naturally. We got the Earth's off ecliptic tilt. In the moon, another thing about the moon does not orbit in the Earth's equatorial plane. It orbits in an off equatorial plane. And in our collision, we got the off equatorial plane. Lots of people believe that there were actually two moons that formed from the impact that later coalesced into a single moon. And in almost all of our simulations of this type, we got two moons that came out, the two dominant moons that came out of the collisions and then what happened, either they coalesced or one moon drove the other moon into the Earth and eliminated it. So we got the companion moon, and they believe that it was a very violent collision and a lot of violent mixing, which you can tell by our simulations we had that. So we're after three things, and then other things we weren't after just fell into place, which are unanswered questions. And so we figure we're on the right track. Now, so that set of students graduated, and we thought, had we answered all of the questions about the giant impact hypothesis? Well, we thought there is a big thing out there. It's called the sun, and it's 99% of the mass of the solar system, and that hasn't been in any of the simulations. So we wanted to add the sun to our simulations and see what happened. So what we did, we took the initial conditions from the last project, added the sun, and ran our initial conditions backwards to see where these two planets originated. And they should originate with inside the asteroid belt. And then we ran it forward and then saw what type of orbit ended up happening. And we got a nice circular orbit around the sun. And here's their simulation.
One day you look to see I've gone, for tomorrow may rain, so I'll follow the sun.
And the red dotted line is the asteroid belt, and the blue and green arcs are the two planets. We ran backwards what their orbits would have been before they collided, and you see they were well within inside the asteroid belt. And that was 10 years worth of work and 4 generations of students. So that's basically an overview of the giant impact hypothesis and our late lunar forming impact simulations. If you want to see a full video of the collision, the third set of students collision where they got all the 7 properties that people are looking for, that's at the end of this section. Thank you.